common element between these two sets. So let the element in here, it'll be of the form xih1, right? This is a member of this set. And let the member of this set, it'll be of this form, okay? Because we're assuming there's at least one element that's in common between these two. And if that's the case, we can draw some conclusions, right? So the element in that one that's equal to an element in this one, you'll have it in this form equals in that form. Now what? So post multiply by H2 inverse both sides. This will cancel. You get this, and H2 inverse goes here. So you get this, all right? And now pre-multiply, in other words on the left-hand side, by xi inverse, so that'll cancel, and you get xi inverse here, right? So you're left with h1, h2 inverse on this side, and xi inverse xj on this side. Now, this here belongs to H, right? H is a subgroup, therefore it's a group, therefore it's closed, and therefore this product here belongs to H because H is closed. So this belongs to H, and therefore this belongs to H. All right? Now from, I've rubbed it off now, but previous theorem 46, the first part, 46.1, if that belongs to your subgroup, then theorem 41 says that xih equals xjh. Go back to the previous part, previous session. All right. So if that's true, then this is true. Okay. Now, so that means xih is equal to xjh. Now, what does that mean? How do you interpret that? What is that saying? It's saying that this coset is equal to that coset, right? So in other words, if there's at least one element in these two cosets, they are the same coset, right? So if there are no elements in common, well, by definition, they are disjoint, okay? So if you have no elements in common, they're disjoint. If you have one or more elements in common, they're the same coset. Follow that? All right. Therefore, here we have a union. Like if they're the same, like if some of these have an element in common, let's say these two, well, they're the same coset. So we can throw out one of the repeats. We can throw out the repeats. So what you're left with, each coset that's not a repeat is disjoint from all the others. Okay, and what I just said is critical. Okay, so each coset that remains in this union here is disjoint compared to all the others. Right? Each coset, after you throw out the repeats, you know, after you get rid of the ones that are the same, so that only leaves disjoint cosets. So that means your G here, your group here, is a union of disjoint cosets, or left cosets, because we're talking about left cosets. All right, so we've shown that. All right, now we've got this critical proof under our belt. We can move on to the big one. You know, one of the most famous results in finite group theory, Lagrange's theorem, which simply states that the size of your subgroup divides, or is a factor of, same thing, that this divides the size of your group. Or in other words, the order of your subgroup divides the order of your group. Okay? So, now let's prove it, and we'll use this to prove Lagrange's theorem. So this one was critical, right? It was a very important result. And we used the previous theorem, you know, using this to get that. So it's all highly structured, right? It's hierarchical. We need this to do that. We need that to prove this. That's the nature of pure math, right? if you like this kind of thing, I talk about at higher levels. If you keep following me to higher levels, we will build cathedrals of mathematical logic. It just gets more and more powerful and bigger and more marvelous structures. You can wax poetic. Okay. All right. So let the order of your subgroup be M. Let the order of your group be N. Okay. And Lagrange's theorem simply says that N is a factor of N. M divides N. Okay. Now how to prove that? Well, let's see. Let this be your subgroup, right? Put an M here because we assume the size of your subgroup is M, right? So you'll have M elements by definition, right? What is the order of a group? What does that mean? It just means the number of elements that it has. Okay? So the order of this is M. So here are your M elements, M different elements, right? It's just a set. So they're all different. Okay, so X of H. Well, you just there's your left coset. By definition, you just X each of these on the left, right? You get that. Now each of these X, H are all distinct because if they're not, each of these are different from each other. Because if they're equal, then you could pre-multiply by X inverse, both sides, and then you'd get HI equals HJ. But no, that's a contradiction. Each of these elements in the subset H, so in the subgroup H, they're different. Okay, so each of these is distinct. Now look, how many elements do you have in X of H? How many elements in the coset? Well, the same number as in the subgroup, right? Look, H, they map 1 to 1, right? So the number of these is equal to the number of these, and vice versa. All right. So the size of your H is equal to the size of your XH. So in other words, the size of your subgroup is equal to the size of your coset, right? And they're both M. M is the order of your subgroup, right? So you've got that. Now look, from the previous theorem, your group is the union of disjoint cosets. So here's your coset. Now, how many? It doesn't really matter how many there are. You'll have usually several, at least, disjoint cosets in your group. So now it's just a set, so you can unionize all these sets, and let's say there are P of them. Right? P distinct or disjoint cosets, right? And G is the union of those, disjoint. So if you take the size of G, so you take the size of the left-hand side, we'll give you the size of the right-hand side. Well, that will, now because they're disjoint, right? They have no elements in common. So you can find the size. So taking the size of G is effectively equal to this, right? So I could put a mod sign here, the absolute value of, the numbers of, but because they're disjoint, that's the same thing as, perhaps I should have written this out a few more lines, but modding G, meaning find the absolute value of, or the size of, is the same as doing this, but that's the same as the union of this, because they're disjoint. So you get this kind of thing, all right? Now, what is the size of a coset? Well, it's just M, right? But you've got P of them, P disjoint cosets. So this sum here will just be P times M. Now this is M, right? And you've got P of them. And all of these cosets have the same size, M, right? And you've got P of them. So this sum here is just Pm. And therefore the size of your group, G, is just Pm. But what is M? M is here. M is the order of your subgroup. right? It's the size of your subgroup. So instead of having PM here, you can write P size of H, or P order of H, order of your subgroup, right? So the size of G is equal to some integer times the size of H. So that means that size of H, that was the order of H, is a factor of G. It divides G, see? So there it is. The order of your subgroup divides, or is a factor of, the order of your group, the parent group. And there it is, one of the most famous results in all of finite group theory, Lagrange's theorem. And we will, believe me, we will use this result again and again and again. It'll be second nature to us, right? And it's easily stated. Look, it's just very very simple concept. All right. Now, with that under our belts, we can immediately start getting some consequences from it. So one of them is that so there's the next theorem. Take any element from your group. And let k here, little k here, be the order of that element. Now remember the distinction between the order of an element and the order of a group, right? Order of a group, number of elements it has. Order of an element is some